I know it's just 7:30. We'll probably wait another minute or two just for people to start, to continue trickling in. I know it's just 7:30. We'll probably wait another minute or two just for people to start. Maybe one more minute, then we'll start. All right. Well, Ahmed, are you ready for me to start my intro?
Yes, I am.
Okay. Well, then we will start. So good evening, everyone. Hello to everyone who's watching on Zoom. Hello to everyone who is watching on YouTube. Welcome to the 2021 public lecture of the TASI Summer School at CU Boulder. So the TASI Summer School is an institution in Boulder and in the theoretical particle physics community. It is, in my opinion, the best summer school in theoretical particle physics around. And we have one of these public lectures almost every summer. We missed last year because of the pandemic. The school did go on. The school went on last year and also this year online. It's 4 weeks of some of the best young graduate students in the country and sometimes the world coming to learn about cutting edge things in theoretical physics. And as part of that, we like to have one of our lecturers speak to the general community, because we know there's a lot of interest out there in the community about what's going on in theoretical physics. And we like to help sort of address that curiosity. So that's what TASI is. My name is Oliver DeWolf. I'm a professor at CU Boulder. And tonight we are extremely pleased to have with us our speaker, Ahmed Almheiri. Just to give you a few words about Ahmed. So he is from the United Arab Emirates, and he's told me that he is, to his knowledge, the first theoretical physicist from the UAE. Ahmed came to the US to get his PhD. He studied at the University of California, Santa Barbara with Joseph Polchinski, who some of you may remember as the speaker at the 2015 version of this TASI Public Lecture. Ahmed also worked at Stanford University and then moved on to the Institute for Advanced Study at Princeton, where he is now. He recently became the winner of the 2021 New Horizons Prize in Physics. So the citation of that was for calculating the quantum information content of a black hole and its radiation. And this ties in very much with what we will be hearing Ahmed talk about tonight. He is one of the leading people in the world pushing forward our understanding of black holes and Hawking radiation. And I'll also mention, since I mentioned his PhD advisor, Joe Polchinski, who sadly passed away a few years ago, Ahmed is also currently editing an upcoming published version of Joe's memoir, which will be called Memories of a Theoretical Physicist, A Journey Across the Landscape of Strings, Black Holes, and the Multiverse. So that will be appearing. Joe already had a sort of draft version online at the archive repository, which many of us have read and is really great. So I'm looking forward to that as well. All right, so with that, I will turn you over to Ahmed and he will tell us about the quantum mechanical restructuring of space-time. So take it away.
All right, thanks a lot, Oliver. It's a great honor and privilege to be giving this lecture on behalf of TASI. And yeah, today I'm going to talk about our evolving understanding of space-time. And this picture right here in the center, this is a piece of work by Kandinsky, and it's meant to sort of represent this restructuring that I will talk about, or at least a modern representation of it. I will go through a sort of the evolution of our understanding of space-time across the ages, starting with sort of the boring and rigid picture proposed by the Greeks, and maybe even was held before them, then to the weird and wonky results or imagination of what space-time is of the 20th century. And then finally, talk about some of the recent ideas, which I can only describe as being crazy. However, before I begin on this journey, let me first describe or summarize the way that physics is done. Broadly speaking, it breaks up into sort of two activities. The first being experimental physics, where the goal is to observe the universe to either confirm or contradict some theory. And this can be done by looking sort of outwards at the stars, and the galaxies and so on, using some sort of telescope, or maybe just doing experiments here on Earth. And this involves, it's very expensive. It involves mega projects with huge machines, such as the one shown on the bottom left. That's supposed to be at the LHC at CERN in Geneva. Or sometimes, maybe you build a multi-million-dollar telescope and then throw it into space. And across the aisle from experimental physics is theoretical physics, of which I am one. And the question of, well, I'm asking here the question, what do theoretical physicists do all day? And what we do typically involves thinking, and then maybe more thinking, and more and more and more thinking. And sometimes if we're not getting anywhere, we seek the help of others and discuss with others. The toolkit for theorists involves two things. The first is a solid foundation in mathematics, which in some sense we've sort of come to understand as the language of the universe, and it's really shocking why it works so well. The answer to that question, I would say, is not very clear. The other tool that's used by theorists is the so-called thought experiment, which is basically an exercise of considering sort of a carefully crafted physical scenario in order to test an idea. And in this talk, we'll see many examples of this. And it's really shocking how far you can get with just these two ingredients. Okay, so now let's get back to space-time, beginning with the Greeks. With the Greeks, they had this notion of an absolute space and time, which Aristotle talked about. He famously had a picture of cosmology of the universe, where the entire universe is centered about the center of the Earth, okay? And everything was in orbit around that. That's the picture here on the left. The Earth is in the center and everything is going around that. All of this, however, crumbled down at the hands of Galileo, building on earlier work and astrophysical observations by Copernicus, who proposed the heliocentric model for the solar system. And so heliocentric meaning going around the sun, you have all the planets going around, and the Earth is somewhere here. It's not in the center in any sense. Sort of fueled by these observations, sort of the paradigm shift from the Earth being the center to it not being the center, Galileo, I believe, sort of had the belief of why stop there, okay? And for him, there was no preferred center. And you can see this from his discussions on this notion of relativity, which might have been proposed before him, but he was the clearest one to state it, which is the statement that the laws of physics should be the same for anyone who's moving at a constant speed. This is often called Galilean relativity. And this is something he could test on Earth. He didn't need to make any observations of the planets or stars or whatever. He used the example of a ship. He said that if you're on a ship sailing the seas, and if you're on a day where there are no waves, then while you're inside the ship, you don't feel that the ship is moving. For us, a more natural, more commonplace thing to consider is the same situation with a train. That's the picture here on the bottom left. The statement is that these two persons inside the train or outside the train, assuming that the train is going at a constant speed, let's say v1, they would experience the same physics. Here they would experience the same laws of motion or the laws of juggling. Furthermore, Galileo considered what would happen if somebody was to run on the ship or on the train, and he deduced that that if you have somebody running on the train, the speeds would compound or they would add. From the perspective of the person standing outside of the train, the person running in the train would run at a speed of v1 plus v2. Okay. And this was sort of the state of the art for our understanding of space-time up until somewhere in the mid-19th century. So the idea was that, what I meant to say was that the notion of space-time didn't really advance much from that point up until the 19th century. So space and time were still rigid, but the main lesson is that there is no preferred center. The main, there is only relative motion. However, this thing started to change as people started applying the principle of relativity to other laws of physics, not just motion. In particular, applying the principle of relativity to the laws of electromagnetism. Something that was discovered in the mid-19th century were the laws of how electricity and magnetism get combined. That's in so-called Maxwell's equations, which basically say that a changing electric field can create a magnetic field, which creates an electric field, which creates a magnetic field, and so on and so forth. And it was then realized that this simply described light. It described light as a propagating electromagnetic wave, and perhaps the most surprising result was that it's a wave that travels at a finite speed given by this value here in miles per hour. The speed of light is often denoted by the letter c. You should keep that in mind. The amazing thing about Maxwell's equations is that they have relativity built in. The equations are the same, independent of what speed you go at, so long as it's constant. And this sort of agrees with Galileo in principle, but it disagrees with him in detail. In particular, the formula for how speeds add no longer applies. In particular, if you have a person inside the train who shines light facing the direction of the moving train, then Galileo would tell you that from the perspective of somebody outside the train, the light would appear to move at a speed of v1, the speed of the train, plus the speed of light when you're not moving. But I just said that Maxwell's equations tell you that no, the speed of light should be fixed no matter how you move. Well, so long as it's constant speed. And this is where Einstein comes in. He too was a staunch believer in relativity, and he understood that it was a bit more subtle than Galileo had sort of conceived. He gave a simple argument on how to save the speed of light by compromising on compromising on the passage of time. Okay, and he based his reasoning on a very simple thought experiment. Again, he said, let's imagine that you have these two people, Alice and Bob. Alice is standing outside and Bob is inside the moving train. And Alice, or rather Bob, has a flashlight directed towards the ceiling, which as the train is moving, he is going to turn on. So let's go through that. He turns on the flashlight, and after some time, the beam of light reaches the screen on the ceiling of the train. Now, from Bob's perspective, the light would have traveled a distance d1, simply the vertical size of the train. However, from Alice's perspective, light would have traveled along this diagonal route of distance d2. And now, if we use the God-given formula relating, saying that time is distance over speed, then which is simply, then we are able to compute two different times, one from the perspective of Bob being d1 divided by the speed of light, or from the perspective of Alice being d2 divided by the speed of light. And then we find that since d2 is larger than d1, this diagonal line is larger than this vertical line, then more time would have passed for Alice than for Bob. Okay, and so this was one result of Einstein's thinking on relativity, and it's part of a larger set of results which he called special relativity, which involves a few more things. So I just talked about time dilation, the fact that time runs differently depending on how fast you move. But there's also length contraction, where objects tend to get squashed the faster they move, and the fact that there's a maximum speed limit, which is set by the speed of light c. And there's also another thing. I went too fast on that one. There's a phenomenon called the twins paradox, which if you have two twins, so two Einsteins sitting together like that, and then one of the Einsteins chooses to move, accelerating away and accelerating back, he would find, well, the time for the moving Einstein, the passage of time for the moving Einstein is slower than for the one that remained at rest, and hence the Einstein that remained at rest would be older. Okay, so the twins would no longer be twins. So so those results remained the same for roughly 10 years or so. And the new notion of now space-time is that, space and time combine to a space-time, and it's less rigid than before. It's not completely wobbly yet. We'll get to that in a second. The next stage in understanding of space-time is to talk about gravity. Really, the story of space-time is also that of gravity. One of the most notable thinkers on the subject is Galileo again, who made the following claim. He said that all objects fall at the same rate so long as you ignore air resistance, independent of their mass. And everyone is familiar with the apocryphal story of him testing this hypothesis by throwing two cannonballs or boulders from the Leaning Tower of Pisa, and then finding that they fall at the same rate. He didn't actually need to do this specific experiment. He had a quicker and frankly much less strenuous method of arriving at this conclusion. What he did was he conducted a thought experiment. Okay. So what he said was, let's suppose that heavier objects fall faster. Okay. Then it follows that an elephant tied to a mouse is heavier than an elephant or a mouse separately. Therefore, the combination of the mouse and the elephant would fall faster than the elephant by itself or the mouse by itself. But then hang on, this is very weird. If the mouse falls slower than the elephant, then wouldn't this mouse slow down the elephant? And so just by reasoning alone, you reach a sort of logical inconsistency or a contradiction. And so what must be true is that the initial assumption was wrong. And so everything must fall equally fast. So that was Galileo's reasoning. Then comes Einstein again. Now he's a bit older, more seasoned, more wise. He came up with a sort of a souped up version of relativity, but now when applied to acceleration. He called this version of relativity the equivalence principle, which is the statement that the laws of physics are the same on the surface of a planet or in an accelerating rocket. Namely, that gravity is the same thing as acceleration. Okay, if you're sort of in the rocket, landed on Earth, or blasting through space, you wouldn't be able to tell the difference. And this would apply to the laws of motion. So if you throw an apple, it would fall in the same way in both situations. But he also got a lot of mileage from studying light in the previous version of relativity. And so surprises come about when you consider light. If you focus now first on the bottom right picture, as you're accelerating, one would expect that light would bend downwards, so assuming that you're accelerating upwards. The reason is simple, I think. Basically, light wants to travel in a straight line, but you're accelerating away from it. So it would appear to bend. But since acceleration is the same as gravity, or gravity is the same as acceleration, light, which should also bend due to gravity, due to the bending of space-time by the planet. And so the picture that he gave us is the following, which is what I just said, that gravity, or rather space-time around a massive object, is bent and warped. And this falling that we all feel if we jump, that's just because the shape of space-time directs us inwards towards the center of this massive object. And it's not just us, it also includes light. Right now, as you're sitting down, you're feeling the force of gravity. That's because you're stopping yourself from falling. And in a sense, it's because you are currently accelerating, not in space, but in space-time. Okay. I guess the best analogy here is that if you're in an accelerating car, you feel a pull backwards. Right now we're sitting down, we're feeling a pull downwards. So it's the same force. Okay. So relativity or general relativity also has its version of the twin paradox. Here, this is our two twin Einsteins. The left Einstein is older. He knows about general relativity, while the right Einstein doesn't. In particular, he knows that there's such a thing called gravitational time dilation, which is the statement that time runs faster in regions of weaker gravity, so farther away from the planet. And so this older Einstein can get back at the young Einstein by going down to the planet, resting there for maybe a few hours, which would be equivalent to a few years for the Einstein far away, and then he can catch up to him. And now they're even. So some history about general relativity. So Einstein, he announced the theory of relativity or general relativity around November 1915, and he declared that this theory is too hard to solve. And then 2 months later, Karl Schwarzschild found the first non-trivial solution in January 1916. So even Einstein can be wrong. And funny enough, Schwarzschild found the solution while he was serving in the military during World War I. He's a pretty tough guy. What solution did Schwarzschild find? Well, he discovered what I would say is the most unusual and the most terrifying predictions of general relativity. Namely, he found the so-called black hole. So what's a black hole? There are many answers to this question. One of them is to say that it's sort of space-time's way of letting you know that it's full. General relativity predicts that that there's a critical radius below which any mass will warp the space-time enough to form a black hole. Okay, so if you squash a piece of matter below this critical radius, which is sometimes called the Schwarzschild radius, you will form this black hole. Here's another picture to just show the same phenomenon, which is that space-time gets more and more warped as you're squashing this object. The steepness of this grid, or you can call it space-time, is supposed to represent the difficulty in trying to escape from the massive object. It's supposed to represent the strength of gravity, in a sense. As you can see, for a black hole, it kind of becomes or tends to become infinitely more difficult. And that's basically this phenomenon of the event horizon, that the space-time develops this region or this perimeter, which is the point of no return. Incidentally, on this slide, assuming all of you guys have, you're watching this on a regular laptop screen, the size of this black hole is the actual size you'd get if you were to squash about 2 Earths to form a black hole. Okay, that's just a side comment. This is the Schwarzschild radius of 2 Earths. The terrifying thing about black holes is that they're real. So on the left, it's a video taken of the center of our very own galaxy, and you see all of these supermassive stars orbiting something, but there's nothing there. Okay, you don't see anything. There's nothing emitting as much light as these stars. In fact, it's a black hole at the center of our galaxy. And more recently, there was this picture taken of the black hole in the center of the M87 galaxy. Um, and you can see it here, this dim region in the center that's supposed to be where the black hole is. It's black. It doesn't emit any light, and this glow around the black hole is the glow that comes from really hot gases around the black hole. What this captures is how the gravity of the black hole bends the light around it. So this light here is actually, it looks like it's above the black hole, but it's actually behind it. But it gets bent so that it reaches us. Next, let's talk about the structure of a black hole. The reason, so people often say that the reason why you can't escape a black hole is that gravity becomes extremely strong. Well, I mean, that's true, but there's a better answer to that, a better explanation for that phenomenon. What happens is that when gravity becomes the reason why you can't escape is because the singularity, the center, the so-called center of the black hole, becomes to your future. So your future is directed inwards, and there's nothing you can do but fall in. In fact, the faster you try to escape, the sooner you will hit the singularity. So if you ever find yourself behind a black hole event horizon, my advice is to just give up and enjoy your last moments of life. Singularity is this funny place where Einstein's theory breaks down. Everything we know about physics breaks down. The force of gravity grows uncontrollably as you approach it. And it leads to many funny phenomena, the most famous of which is spaghettification, where the force of gravity changes so rapidly. I don't mean in time, but I mean distance, that things that are closer to the singularity get stretched much more strongly than things farther away, or get pulled rather much more strongly than things farther away. And so you get stretched as you approach singularity. You also get squashed in the other direction, but let's not talk about that. Okay, so far, so what we learned is that space-time is bendy and warped, and for some reason likes Italian food. And this has been the state of the art for quite some time, until some weird results in roughly around in the 70s. But before I talk about that, we need to take a short detour and talk about something that happened in the 20s. Namely, we need to talk about quantum mechanics, which was discovered, this theory discovered by Schrödinger and Heisenberg. Oh, oops, I think I have, one of my pictures is wrong here. Let me fix that. Okay, no, still not that one. There you go. The actual Schrödinger and Heisenberg, who discovered that the nature of things gets extremely weird once you study very, very small isolated particles like atoms and electrons and light and so on. They found that the physics of the very small displayed a lot of counterintuitive phenomena. One of the more famous ones is this particle wave duality. So on the left here, this is the usual behavior of a wave. You have these crests and troughs, and they can interfere with one another. But the picture on the right is a lot more confusing. The picture on the right is sending one electron at a time through two pairs of slits, as shown here on the left. And you're setting them one at a time, but nevertheless, you get some kind of interference pattern, something that happens when different waves, in the case for just regular waves, it happens when different waves interfere with one another. But something crazy is happening. A single particle can interfere with itself. In some sense, the interference happens between different possible paths for this electron going through the slits. What this sort of, the only way to make sense out of this, as we learned from the work of these two, is that reality is probabilistic. It's not deterministic. There's a probability for the electron to go through one slit or the other, and these two different possibilities can talk to one another. I know this sounds extremely crazy, but the math doesn't lie. I mean, the math doesn't lie. Okay, so let's move on. Then there's another phenomenon of quantum mechanics known as quantum superposition. The most famous example is that of Schrodinger's cat, which can be both alive or dead, depending on whether some radioactive particle decayed or not. There's a much simpler story of this. Let's just let me define something called a quantum coin. So here, a quantum coin is something that can be both heads and tails at the same time. Okay, you can take a superposition of heads and tails. What does this mean? This means that if you were to prepare many copies of the same coin, each of which is in a superposition of heads plus tails, and then you measure each coin individually, you would find different results for the different experiments, but on average, 50% of them will give you heads and 50% of them will give you tails. So the probability of finding heads is 1/2, and the probability of finding tails is also 1/2. Okay. Before you actually looked at what the coin is, it was in a superposition. Just because you found it to be heads doesn't mean that it was heads before that. It was, again, in a superposition. This is really weird, and it really bothered Einstein and his friends, Podolsky and Rosen, very much. Through their worry, they discovered this phenomenon of quantum entanglement. They said, okay, we know about the case of one coin being heads and tails, but what if I have two coins where I have 50% chance of probability or 50% chance of finding them to be both heads and 50% chance of finding both to be tails, with 0 probability of heads, tails, or tails, heads. So what this would mean that if you have 4 copies of these two coins and you check on them, you look at whether they're heads or tails, you'll find that they're always the same. Okay, but it's still probabilistic, but nevertheless, if you know the result of one coin, you know the result of the other. This is very disturbing to these 3 people because this is true even if the 2 coins are extremely far away. You can put one in this galaxy and it can be entangled with a coin in another galaxy, and nevertheless, they would still be correlated. Einstein called this a spooky action at a distance. The action here just means that knowing the result of one completely determines the result of the other. And this is actually an important point. The issue is that, or an important takeaway from this is that while you don't know the result of the first coin, so you would describe that as saying you have no information with one coin, but having measured the first coin, you can correctly guess with 100% certainty what the second coin will be. I will describe the situation as saying that with one coin, you have no information, but with 2 coins, you have complete information. Okay. All right. Now, quantum entanglement was analyzed or studied for at least 60 years now. And if there's sort of one conclusion from all of this thought, is that quantum entanglement is useful for absolutely nothing. Okay, actually, did I have this right? Yeah, nothing, that's right. What do I mean? Well, nothing in quantum mechanics is actually something. It turns out that in a sort of in quantum mechanics, empty space is actually filled with entangled particles that move together, okay, in this way. In fact, their existence is what makes empty space feel empty. This shading between the two dots is supposed to represent the entanglement. And in fact, these entangled particles appear across any partition. So I was showing one partition here, but you can have something like this. Okay, so these are everywhere. They're in front of you right now, and they're everywhere. And something that we learned in the 70s. Now we're back at the 70s. From Hawking was that this leads to surprising consequences for black holes. In particular, what he emphasized was that there's nothing at the horizon as well. What this means is that given this interplay between these entangled particles and the event horizon, what happens is that the event horizon separates these two particles from one another. Basically, the green particle outside, it gets separated from the orange guy. The green particle flies away, and for some technical reasons, it has positive energy as it goes away. So it carries positive energy as it's floating away from the black hole. While their inside partners that they're entangled with, they fall into the singularity and they carry negative energy. Okay? Again, this shaded gray line connecting the two particles is supposed to represent entanglement. Okay, let's the punchline from Hawking is that this leads to black hole evaporation. So let's watch the process of black hole evaporation in the coming slides. But before we do that, let's imagine we throw a letter into the black hole and then watch the black hole evaporate. So we throw the letter in, and now, so the black hole emitted sort of one particle. Then when it emits a second one, the size of the black hole gets smaller because more and more of these orange particles are quote unquote created, which because they have negative energy, they make the mass of the black hole smaller. So they make the size of the black hole smaller. And then if we keep going, the size of the black hole, I guess I should have emphasized that by the size of the black hole, I mean the size of the event horizon. That's the shaded blue region. It gets even smaller still. And if once it evaporates enough, it simply detaches from the original spacetime. Okay? And it just floats away. We can just ignore it for now. So what it looks like for somebody observing this black hole is that the black hole and the letter just disappear, leaving behind these green particles. Now, I want you to recall something from the quantum coin, entangled quantum coin example, that you should think of the radiation as sort of composed of one half of a collection of entangled particles or coins, and this half contains no information, in the sense that that if you do measurements on these particles, you get random results. In the same way that when you did measurements on one coin, you got random results. This is the famous information paradox, which is a conflict between quantum mechanics and space-time. So it's an inconsistency that arises from trying to have a quantum mechanical description of space-time, in this case, black holes. And you might ask, why is this a problem? Well, for ordinary processes, for example, if you just simply take the letter and you burn it, in principle, you can reconstruct the contents of the letter by just collecting the emitted photons and maybe some of the ash that's left behind, and should be able to reconstruct the entire letter with all of its secrets. But in the black hole example, something weird was happening. It looked like the final radiation, well, it was random, and it seemed like it doesn't know anything about the letter that we threw into the black hole. So you can ask, where's the information? Well, it looked like, at least in this dynamical picture that I had of the black hole evaporating, the inside of the black hole, rather the black hole interior, branched off into a separate, quote unquote, baby universe that is disconnected from our universe. And the information about the letter is not in our universe anymore, it's inside the baby universe. But from the perspective of it really looks like from the perspective of someone in our universe, that information is lost. There's this idea due to Gary Horowitz and Juan Maldacena of trying to get back the information from the baby universe. And it used something from quantum mechanics known as quantum teleportation. So the idea is, let's imagine you have 3 coins and you want to teleport the information from the first coin to the third coin. Okay? Let's imagine that 2 of the coins are entangled and the first coin is, let's say, in a definite state to be heads. The total state of the 3 coins looks something like this. It's heads, 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 plus heads, tails, tails. Okay, notice that the second 2 coins are entangled. The statement of quantum teleportation is, if you force the first 2 coins, well, there's a way of making of ensuring that the measurement on the last coin that it gives you heads. The way you do that is you force the first 2 coins to be heads. Notice, if you force the first 2 coins to be heads, then the third coin is definitely a heads. Had you forced the first 2 coins to be heads, tails, then the last coin will be tails. But that's not what we want. This forcing thing is actually not sort of technically correct, but I'm just trying to just deliver just to deliver the message. This is a very simplified version. And the idea, according to these 2 people, is that maybe space-time implements a kind of teleportation, that perhaps the singularity could do or could perform some sort of forced measurement on the letter and one member of the entangled particles, the orange particle. So if you measure these 2 guys, then the idea would be that the information from the letter can flow out using the entanglement between the 2 particles, the orange and green particle. So in some sense, entanglement is a bridge from the inside to the outside. And some really exciting recent results support this idea on some more ground footing, at least mathematically, that quantum gravity implements a kind of quantum teleportation. And it really goes, it goes quite far. It tells you that first, entanglement is a feature, not a bug. And a surprising conclusion is that using this entanglement, in some sense, you can reach into the baby universe or the black hole interior by carefully doing experiments on the radiation or these green particles in our universe. In a sense, like a cartoon of this is like having a marionette or a puppet that you can control the puppet via the entanglement from the sticks, or rather by these strings that are connected. They're connecting the puppet to the sticks. These strings are the analog for the entanglement. So in some sense, well, because you can control the inside of the black hole from the outside, it looks like it seems like the inside of the black hole is in some sense part of the outside spacetime. And these are some crazy ideas that we're trying to understand better these days. Now, so the punchline at the end of this timeline that I wanted to consider was that large space-time distances, or sometimes even connections between spacetimes, can be bypassed using entanglement, something which I can only describe as crazy. And so the structure of the spacetime that we've come to understand is that it's a lot more intricate and it's a lot more interconnected than we used to think. And I think a great picture to summarize everything I told you today was to go full circle to the very first picture I showed on my first slide, which is to go back to Kandinsky. So let me stop there. Thank you for your attention.
All right, well, thank you very much, Ahmed.
Thank you.
So I should have mentioned at the beginning, but didn't, that we're happy at the end to take questions. We have people on Zoom, we have people on YouTube. If you raise your hand on Zoom, I can allow people to speak if you have questions. People on YouTube, you're welcome to submit questions to the chat and they will be relayed. It may take a minute or two, but we'll try to get some different kind of questions. Okay, well, maybe I'll start out. I don't see anyone raising their hand on Zoom, but I see a question coming from YouTube. This is from Brandon Thornton. Why do the entangled particles substaining the vacuum move together? That's the question.
Good question. Fortunately, I don't think I have a good answer to that. It's somehow to preserve something called well, it's just to preserve the symmetry of space-time, in a sense, that these particles have to move together so that no matter where you look at them, it always looks the same. I think that's the quickest answer I can give you.
Okay, I see a question that was typed in on the Q&A. You're welcome to type in questions that way or over chat as well. So this is from Michael Donahue. Under what circumstances is quantum entanglement enabled or required?
So quantum entanglement is a robust prediction from quantum mechanics, and it is something that you can actually prepare in the lab. Like there have been many experiments that have prepared particles, entangled particles. So it is definitely something that you can engineer by hand. But it does turn out that in complicated systems that involve many particles and so on, entanglement is actually like it's a thing that just the natural dynamics of the system likes to create entanglement. Namely, if you have two particles that are not entangled and they somehow interact, just by mere interaction, so they interact and then they separate, by that interaction, they get entangled. It's a very generic thing that actually happens very easily, and it's actually connected to, in a subtle way, to like the second law of thermodynamics, that things get more and more complicated, but sort of the quantum mechanical version of that. You can say things get more and more entangled. That's one version.
Okay, I see a few more questions. So one comes from Trevor Sesnich. The question is, could you add more detail as to why particles falling into a black hole have negative energy and why the ones leaving have positive energy?
Okay, good question. I would say, I think I can only give the usual answer that's given to this, which is it has to do with this fact that that inside the black hole, time points towards the singularity. In some sense, only in some sense, the orientation of time inside and outside is kind of different from one perspective, and it just so happens that it's that perspective that determines the sign of the energy, whether it's positive or negative. So it has to do with the structure of space-time, or rather, as you compare the structure of the space-time just behind the horizon and just outside the horizon.
All right, these are some great questions. I see another one from Tommy Chin. From my understanding, for quantum teleportation, we need a classical signal. Is that still true here?
Oh, excellent question. Okay, so now I can expand on this. I wanted this question. Okay, so in regular teleportation, you have, you do a measurement, and given the result of that measurement, you send the result of that measurement using classical information, and then you can do an operation to extract the message. That's standard teleportation. In the case of a black hole, the measurement that I talked about it's not that the singularity does a measurement with several possible outcomes, but rather that the singularity is a final, sometimes we call it a final boundary condition. It selects the result of a measurement. So you already know which measurement is going to happen, let me correct my sentence. It's not that you know which measurement is going to happen, you know which result is going to come out, and therefore you don't need somebody to send you classical information. You know what the result is going to be, and then and just using that, you can recover the information on the outside. In some sense, the result of the measurement at the singularity is part of the specification of the laws of physics inside the black hole. Finally, let me just make a comment that we still don't understand this aspect as well enough as we should, or definitely not as much as we understand regular teleportation. And I would say understanding the details of that is still a work in progress.
All right, so we're getting more and more questions. So if you've asked a question, we will try to get to it, but it may take a few minutes because there are a number now. So I have one coming from Kurt Nordbach asking, I think several of the conclusions are based on conservation laws, energy and information. How do we know that these laws are valid? i.e., why do we choose to keep these laws versus other things?
Excellent question. And well, you can assume that these laws don't apply. So you can do what Galileo and what Einstein and what all of these people did, which is to consider a thought experiment. So there have been many such thought experiments where you posit that energy is not conserved or that information is not conserved, and then you run into contradictions. Things that can be ruled out very easily. Well, you run into logical contradictions, but you also run into experimental. You run into you make predictions that you can easily falsify experimentally, and the best mathematical frameworks that we have for describing physics as we see it has these notions, energy conservation and information preservation, as sort of caked in. Like it, well, but it's not that you put it in by hand. It's hard to come up with a mathematical framework for physics that does not have these principles automatic. Let me put it that way.
Okay, great. Let's see, I'll do one more question from YouTube, and then I also see a hand up, so that'll be second. So first, the YouTube question. Have we been able to separate the complementary probable half particles in a lab, the quantum outcomes?
Sorry, can you read that question one more time?
Yeah, have we been able to separate the complementary probable half particles in a lab, the quantum outcomes?
I'm not sure what is meant by, I'm not sure I understood the question entirely. Maybe you mean,
I would probably parse it as just, can we separate entangled particles in a lab and sort of see them more separate from the other?
Yeah, okay, if that's the question, yeah, that's something you can do easily. I mean, we know how to take two unentangled particles and then make them, and then entangle them. And we certainly know how to do the reverse. In fact, there's actually an easier way. You start with an entangled set of particles, and then you just measure them. So in the case of, so if you had two entangled particles, heads plus tails, and then you did a measurement, suppose you got heads, well, that's the state of the two particles now. It's heads. They're no longer entangled.
All right, so I see a hand up from Dale Gray. Dale, I'm going to allow you to talk if you want to ask your question that way. Dale, I think you're muted, so you may need to unmute before asking.
Is it unmuted now?
Yes, now we can hear you.
I'm intrigued by the paper of, is space-time a quantum error correction code that Ahmed and others, Harlow, had worked on. And what is this code protecting against? Is it protecting against and kind of ensuring that space-time holds together? Could he try to answer some of those aspects of his work?
Okay, yeah, definitely. So let me go to one of my pictures. So maybe this one here. this is actually an example of quantum error correction in play. What I mean is, so actually first let me make a comment about what quantum error correction is. So if you're trying to build a quantum computer, you need to preserve the quantum nature of the bits or the atoms that you're using in your quantum computer. And to do that, you need to separate them from the environment, or you don't want dust particles to interfere and to get entangled with your atoms and so on. That will degrade in the quality of your quantum computer. Unfortunately, it's really hard or practically impossible to completely have a perfectly secure, clean environment for your atoms. And so instead, you allow for you can sort of try as best as you can, but you'd allow for some interactions between the air and dust and so on and the atoms in your computer. But whenever an interaction happens, a small error is introduced. And in order to preserve the information in the computer, you need to perform something called quantum error correction. The way you do this is, well, if there's an error, you find it and you correct it. One way to do this is to store the information or encode the information in a way that is redundant enough or complicated enough so that small errors don't affect the information very easily. So usually in regular computers, just not quantum computers, just for intuition, for regular computers, suppose I have a bit that's in the state 1, and I want to preserve that it's in the state 1. Something can hit it and it can change it to a 0. So what I do is that I copy this 1 to be many, 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 many 1s. Now, if some of them get affected and switch down to 0s, I can just do a sort of a majority count, and I can recover what the original information is. But for a quantum computer, it's a bit more complicated than that. But it's the same idea. Now let me consider this picture I'm showing on the slide. The information that's being protected here is the letter inside the baby universe. Okay. I said before that during the end of my talk that the inside of this black hole is secretly part of the green particles. So you can learn about the inside of the black hole or this baby universe by doing measurements on the green particles. However, the kind of measurements you need to do are very, very complicated measurements, just something extremely complicated and something that takes a very long time. But it's because of that complexity that the information, that the letter is protected against simple errors that can happen. So if I just take one of these green particles and I play around with it, I hit it, I shine light on it, I do whatever I want, it's not going to affect the letter inside the baby universe. So in some sense, the baby universe is protected against these small errors. And so this picture is supposed to, you can interpret it as a way of providing, or rather, it's a way of protecting against, protecting the message here. Well, I guess I'm just restating what I just said. You're protecting the message inside the baby universe against errors that can happen or interactions that can happen to these green dots. I hope that answered the question. One last comment, maybe just to clarify something. The original paper that you talked about was a set of ideas, the same ideas that I just discussed, but applied to a very, very different setting. But those same principles apply here as well. So let me maybe stop there and take more questions, or maybe you have a follow-up.
All right. Well, we do still have a number of questions, and to everyone who asked one, we will try to get to them. So here's a question from Bob Meinitz. Can two particles become entangled with a third particle?
Yes, they can. You can have, for example, you can have three particles that are heads, 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 plus tails, tails, tails. That's three particles entangled. That's one example. There are many examples.
Okay, and maybe sort of a related question from Aaron Robertson. Can there be a large network of entangled particles that all move together?
Yes, it can happen if you have a large number of, well, one natural way of getting something like that is having a large number of particles that are interacting with one another. They would all be entangled and they would all be moving together as well.
All right, one more from the YouTube chat, and then I know there's a few on the Zoom Q&A as well, and I'm trying to do these in order. This is from Laxbro. If things get entangled just via interaction, why was everything not entangled in the first seconds after the Big Bang?
So I'm actually not, I actually don't know that fact, that that the particles were not entangled at the beginning. Maybe they weren't, I don't know. But that's, I mean, it's a possibility that maybe all the particles at the beginning were not entangled. But it, I mean, it's, it's a mystery. We don't know the beginning of the universe well enough yet. But one can imagine that, sure, maybe at the beginning nothing was entangled because the initial state of the universe, which we don't understand, just happened to be that. But then as things evolve, things interact and get more and more entangled. I'd say we're nowhere near understanding the what is called the Big Bang singularity. This analysis that I discussed here about trying to understand the black hole singularity is sort of a stepping stone towards that. So maybe when I come back and give a talk in 10 years or so, maybe I'll have more to say on that.
All right. So in the Q&A here in Zoom, I see a question from Jason Eckstein. So the measurement outcome at the singularity will be the same regardless of what matter or energy is entering it? And this was asked earlier, so I think this is the black hole singularity.
Yes, yes. The short answer is yes. It's, well, it depends on the total, it might depend just on the total mass that you have, but it would ultimately be the same measurement. That's right. And again, it would be, the guess would be that it's part of the specification of the laws of physics. Once you tell me what the laws of physics are, let's say that's fixed, that determines what the final state, or the state, the measurement rather, on the black hole singularity.
Okay, here's a question from Jim Coviello. If entanglement is real and understood, shouldn't we be able to communicate faster than light?
Excellent. Regular quantum entanglement, just regular, as in just quantum mechanics without gravity, there is no, you cannot communicate faster than light. And that's an established fact. It's a mathematical theorem. You can't get around it. So when Einstein originally said he complained about there being spooky action at a distance, that was a bit unjustified. There isn't really action in regular quantum mechanics. However, that being said, if gravity is in the mix, the last things I told you actually do imply that you can communicate seemingly faster than light using entanglement. However, it appears in very sort of constrained situations, like, for example, the picture I show, picture on the slide. You can communicate to the inside of a black hole, somewhere where, the problem. Well, let me say. Let me add a comment. So the problem with faster than light communication is that you can run into paradoxes, because you can end up sort of killing your own grandfather and so on before your father was born. But in these constrained situations where the place that you can communicate to is the inside of a black hole, it turns out that these experiments where you try to violate causality and construct what is called a closed time-like curve and so on, closed time-like loop, is unachievable. I don't want to say that it's a theorem, but I would say that in all the present examples for which this faster than light communication via entanglement has been demonstrated in gravity, no problems have been found. But if there is a problem, I would say that's that's good news, because then we'd be learning something new.
All right, I see just, I guess, 3 more questions, and we will probably end this at 9. These have been some great questions, by the way. Thank you all very much for all these really thought-provoking questions. We'll probably end this at 9 just to have a conclusion, but in the meanwhile, I see a couple more. So this is from Wes Burseth. Would there be a difference between a 2-particle entangled state and 1 particle evaporating, and a multi-particle entangled state and 1 particle evaporating? That is, what is teleported?
Can I ask you to read that question again?
Yeah. Would there be a difference between a 2-particle entangled state and 1 particle evaporating, and a multi-particle entangled state and 1 particle evaporating? E.g., what is teleported?
I'm going to interpret this as saying, if you have a black hole that's made up of 2 particles versus having a black hole composed of many particles, well, this teleportation, well, it's kind of a I would say ultimately there's no difference, because you would have to wait until the entire black hole evaporates. So whether it's 2, 5, 10, I don't think it really matters that much.
All right, question from Tommy Chin again. When you mentioned that we can't get the info of the orange particles by measuring the greens, is that because we don't know the correlations / entangled states of the pairs beforehand?
Well, let me go back a few slides. If we are, sorry, this animation is going to take a while. Sorry. If we're in this situation, we just have 2 particles that are entangled. If you know one of them, then you know the other. So I hope that answers the question.
All right, one on the Q&A, also from Jason Eckstein. As a black hole shrinks and the event horizon area gets smaller, can the information on the surface exceed the Bekenstein bound? And if so, is that another paradox?
Okay, man, this is a very advanced audience. Okay, this is great. So I didn't talk about the Bekenstein bound. So let me go down. So so if we consider the final stage, well, just before the final stage, this is a situation where it looks like the amount, well, even though in this cartoon I only have three entangled pairs, but in a more realistic setting, the amount of entanglement between the outside space-time and the inside of the black hole can be larger than the area of the black hole. Okay, this is actually the more careful statement of the information paradox. Okay, well, it seems to say that a black hole can have it's a statement that the black hole is storing more information than is physically possible. The area of the black hole is supposed to tell you the total amount of space that you have inside the black hole. So the area of the horizon is supposed to be like the total amount of space inside the black hole, the total memory in some sense. In fact, let me give you an even worse situation, just to make your question even more stark. This situation, this black hole has no horizon, yet there's entanglement. So the Bekenstein bound would tell you, or the Bekenstein bound would tell you that you should not have any entanglement. Okay, and it turns out that this picture, like the thing that I alluded to in the last few slides, is that this picture is misleading, even though it looks like this entanglement violates the Bekenstein bound, but because of the measurement that happens at the singularity, or the measurement between the letter and everything else, that entanglement isn't really counted in some sense. There isn't actually entanglement between, well, secretly, there isn't actually entanglement between the inside and outside. That's sort of the main takeaway. Although it's really hard to explain the details, I think that deserves a completely separate talk by itself. So please excuse my very shallow answer to that.
All right, so there had been a follow-up from Jim Coviello, I think sort of expanding, but I think Ahmed got to these things by the end about faster than light communication. There's a question from Neil Thace. Are the varying light speed theories for quantum space-time being researched these days, or are they proved somehow inconsistent?
I don't know of an example where it's consistent. Yeah, the only way that light can have a slower speed is if it's sort of in a medium where it's interacting with a lot of particles. So then that slows the light down. But I think there are principles that say that the speed of light is it's what it is, and it shouldn't change, assuming that it doesn't interact with anything else. I think that's the state of the art.
All right, I think we're gonna do one last question. So this last question comes from Dale Gray. Can the major equations of general relativity be derived from a quantum mechanical view of space-time?
The equations of, well, good. I think that's, okay, good. The question here, well, the question is, what do you mean by a quantum mechanical picture of space-time? The only theory that comes close, well, the closest that, well, I would describe it as our leading theory for quantum spacetime is none other than string theory, and indeed in string theory, general relativity just pops out. It's automatic. I would say in that sense, the answer to your question is yes.
All right, well, we are going to stop there. I know we're not all physically in one place, so we can't stand up and applaud, and we're not, because of the structure, Ahmed is not able to hear that applause, but I would like to thank him very much for this excellent talk and this really wonderful answering of a lot of really great questions. So thank you everyone very much for coming out to watch. Thank you, Ahmed, very much for this fantastic talk. This was great, so thank you so much.
Thanks, it was a pleasure.
Great. Good night, everybody. We will shut it down here. Take care. Thanks for coming.